Section 4.2 continued our discussion of divisibility, basically. We talked about some divisibility rules in 4.1. We talked about them both specifically, like how to decide if a number is divisible by 3. And we talked about them sort of generally by saying if a number is divisible by A and another number is divisible by A, and for their take their sum or their difference, and we can tell they're divisible, things like that. This is actually going to develop this a little bit further. So we're going to talk about prime and composite numbers. I actually used the word prime last time in a little bit different context, and we may encounter that again in this lesson or maybe in lesson 4.3. So to start with, a prime number is any positive number with exactly two distinct, what's the word distinct mean? Nope, not in the context we're looking at anyway. Specific, particular, those are both true. In particular, we actually are talking in this case about different numbers. They are distinct, they are different. Okay, so there are two different factors. So when we're looking at prime numbers, the reason I mentioned that, the number 1 is not prime. Why not? Because the only factor that 1 has is itself 1. Okay. It doesn't have two distinct factors, it has exactly one factor. So any positive integer with exactly two distinct factors or distinct divisors. So give me some prime numbers that you remember. What's the smallest one? Smaller than 3. 2 actually works. 3 is the next one. What would come next? 5? 7 works. 11. Yeah, we excluded 9 because 9 could have 3. It does have 3 as a factor. The next one is, we'll do a couple more. What's after 13? 17. 19. What do you notice about all of them except for one of them? They're all odd. There's only one of them that's even, right? Number 2. Why would that be? Yeah, because all the other even numbers would be divisible by that number 2. I mean, in reality, the reason that the numbers that are even are excluded is because they're multiples of 2. Notice all the multiples of 3 except for 3 are also excluded, aren't they? All the multiples of 5 except for number 5 are also excluded. That's why the evens are excluded except for the number 2. A composite number then is simply any integer that has more than two distinct factors. So let's give, they don't need to be necessarily in order, but give me some examples of some composites. Give me one, Taylor. Composite number. 6. 6 would work. Because 6 can be made up of 2 times 3. It has more than two distinct factors. What else? 10. 8. So far you guys have given me all evens. Are they all even? 15. 9. Right. So they're not all even, right? We can definitely have some odds in there as well. So we're looking for anything that has more than itself and 1 as a factor. And of course the number 1 is excluded from both of these lists, correct? It doesn't have more than 2 factors, and it doesn't even have 2 factors. 1 is neither prime nor composite. Alright? Important to remember. And it actually, it seems like, so what? But it actually really matters because of some other things we're going to do with it, and I'll show you when we get there why that matters. So factorization is the next idea, and we're going to be working quite a bit with factorization both in 4.2 and in 4.3. Factorization is the ability to take a number and break it down into smaller factors. That is to be able to write it as a multiplication of 2 other numbers besides 1 in itself. So if we were to take the number, let's say 20 or 12, that's what I have written down here. 12 can be written how if we break it down into factors. There's more than one option. What's one option? 4 times 3. How else could 12 be written? 6 times 2. Those are actually the only ways that we can write it with 2 factors, neither of which are 12 and 1. We can write it with 3 factors. How could we write the number 12 with 3 factors? 3 times what? No, I don't want any ones. That would work. 3 times 2 times 2. So if I exclude the number 1 from being able to write these down and list as a list of factors, then what happens is I actually have a listing, I have the ability anyway, to break them down into factors that are all prime. 3, 2, and 2. And that's what prime factorization is. Prime factorization is a factorization containing only prime numbers. It may or may not just have 2 of them. It may have, in this case, there was 3 of them. Okay? Now, this is actually, let's see what's on the next slide. It's a little bit later. Let me mention it now here. This factorization is unique. There's only one way to break the number 12 down into prime factors. And that's exactly the reason that number 1 is excluded from the prime factorization, the prime numbers list. Because if we were able to include, or if we included 1 as a prime factor, then there's lots of ways that we could write the number 12 as a list of factors. So consider this. So if 1 were prime, then we could write down that 12 is 2 times 2 times 3, which we just did. But we could also write down that 12 is 2 times 2 times 3 times 1. And we do not have the same factorization. They would both be primes, if 1 is in fact a prime, and they're different. They're different lists. That's not good. We would like to have one distinct way to do that. And we will find a factor, the prime factorization theorem, which is on your next page, that actually says that we have the ability, in fact, to write them as a list, unique list of prime factors. All right, so we're going to find the prime factorization for each of the following. The first number is 23,660, and I'm going to show you how to do this in 2 distinct ways. So, somebody tell me one way that you've done prime factorization before. Trees. And trees are probably the most common one that people have seen when they arrive in this classroom. So, let's do a tree. There are some nice things about trees, and then there are some not so nice things about trees. The nice thing about trees is that you can choose any 2 factors to start with. So, what is a number that would divide these? It doesn't have to be prime. 10. And 10 is a really good choice to start with because I see the ending 0, right? It sure is. So I can put 10 here, and what would the other number be, Brianna? 2. Right, 2, 3, 6, 6. So there is this really nice ability with these trees to be flexible. And you wouldn't have to have started the problem this way, would you? No, but it's one way we could start. If the factor itself that we've broken these into is not prime, we do the word process again. So 10 can be broken down into 5 and 2. And at that point, 5 and 2 are both prime, so that branch of the tree stops. 2366 is not prime, so we're going to break it down again. So what's the number that will divide 2366? 2. Okay. So what is 2366 divided by 2? Okay. 2 is prime, so I don't need to continue that branch. 1183, what about that one? Is that prime? Well, it's not even, right? So it doesn't divide by 2. Does it divide by 3? So Carly's checking for us with a calculator. How could we do it if we were wanting to just check it real quickly without the calculator to know? Add the digits together. Audrey, did you add those digits together? 13, so that one doesn't work, so 3 is not good. So we're sort of in our mind, we should be going up the list of things that might work. We can exclude all the even numbers. I don't need to test them because 2 didn't go in, right? 3 didn't go in, 4 is even. How about 5? Does 5 work? No. 6 is even, so how about 7? Did 7 work? 169. Okay, 7 and 169. 7's prime, 169 is not, but you might recognize what 169 is. 13 squared. So 169 is 13 times 13. If you didn't recognize that about 169, you'd just try the numbers again. You don't need to try anything when there's 7 because we already said 1183 didn't work with any number below 7. So 169 won't either because it was brought about by doing that factorization. So we start 169 again with 7, we test 7, doesn't work. You know, test it even, so 8, we don't need to test 9, we don't need to test because 3 didn't work. 10's even. 11, we could test 11 and we would find 11 didn't work. When we jump to 13, we would find it did. So even if you don't recognize the number, you can get there. Here is the innate, I don't want to say problem, but one of the drawbacks anyway, one of the cons to using this method, is that because of how it's structured, that is, it's very free-flowing, it's really easy to overlook one of those factors at the end of the tree branches. So you need to be very aware and very careful to get all of them included. We need the end of every branch to be included when we write my prime factorization. Now, when we're writing the prime factorization, what you will see, your book do, and I would ask that you do it as well, is they just go in order from smallest to largest, so that we're all doing the same ordering. So you notice there's two 2's, so they would write that as 2 squared. That's 2 times 2, 2 squared. So I've taken care of my 2's. The next number is a 5, so we do times 5. You can do a dot or you can do an X, which means it really doesn't bother me. The next one then is 7, so times 7. And then I've got times 13 times 13. And instead of writing 13 by 13, which is what I just did, we can write 13 squared. Make it a little bit more concise. Did anybody else learn any other way of doing prime factorization besides a tree? Let me show you one that I encountered when I got somewhere in high school. Not because it's a high school concept, because that's when somebody actually said, hey, you could do it this way. Okay? So there's nothing about what I'm doing that makes it high school content. It's definitely something that I encountered when you encounter trees. You can either do this from the bottom, or from the top down, or from the bottom up. I'm going to go top down, just because when we're working on paper, if we start at the top and we move down, that's sort of our logical progression of information when we work on paper. But sometimes you'll see it drawn from the bottom up. So this is the number 23,660. And what I'm going to do is I'm going to divide. So this looks like division upside down. And the way this works is you divide by the smallest prime number possible. And the ordering of this is important so that we don't forget anything along the way. So what is the smallest prime number that divides this? 2. So that's where we'll start. So what is 23,660 divided by 2? Is that right? 11830? Okay. Which is still even. So we would do the thing again with the number 3, or with the number 2, excuse me. Is it still even? 2 is still the smallest number that divides it. So the division, the factors are actually going on the left-hand side, okay? And then we're going to do the division. We don't have to worry about remainders, right? Because the whole point in doing this is that there aren't any remainders if it goes in evenly. That's kind of nice. All right, so 11,830 divided by 2. What does that give me?
15.
50 what?
9, 15.
Okay, it's all good, everybody? 59, 15. Okay, so it's no longer even, correct? So I no longer have to worry about the number 2. What's the next prime number that I would want to worry about? 3 would be one I would check next. So add those numbers together, 5, 9, 1, and 5. What is the sum? What is it? 20. Does 20 divide by 3? Then 59, 15 won't either. So then we would go to 5. Okay, so we don't want to, the reason we don't want to skip any steps is because when we're done, this is already in order for us, which is really nice. All right, 5 would be the next one, and 5 definitely divides this since it ends in 5. What will it be when we divide? 1183. All right, I don't need to test 2's or 3's or 5's. I've already done that, right? And this number is not divisible by 5, so we just keep going up. What's the next prime number after 5? 7. So we try 7, and we know, because we've already done it once before, that 7 does in fact work. What does 1183 divided by 7 give you? That's that 169. 169 is not prime, but we don't need to test anything lower than 7, so we do test prime number 7 up. 7 doesn't work, 11 doesn't work, 13 would be the next one, and it does. So we've got the 13 and the 13. So our answer's right here. There's no searching, there's no missing, they're all just right there in order, and that's kind of nice. And of course it works out to be in the same list of prime factors for the prime factorization, right? All right, so I would definitely say as far as pros that this is a very organized structure, right? Now, for me, that's a pro because I'm a very organized person. I like things to be very neat and tidy. Some of your students are not like that, and some of you may not be definitely hampers your freedom, right? It's got a very distinct method of what we're doing. So it eliminates the ability to say divide by 10. That would work with this, right? Because 10 is not a prime factor. But it also has, because of the nice neat structure, it has the ability that when you're done, all of the solutions to the equation, or to the, not the equation, but to the problem, are all right there together, so there's no accidentally missing a factor. I want you to be aware of both of them because you will have learners who will like one method versus the other because of how they think. So it's good to be able to present both options, especially if one student seems to be struggling with always missing one of those numbers at the end of a tree branch, right? Or if the fact that they've got so much freedom gives them no place to start. Have you ever had people like that where they're like, I can start in so many ways, I don't know what to start with? Well, the second method actually tells you exactly what to start with. Okay, so there's a couple of different options. All right, now these look a little bit different. Direction says the same thing, find and prime factorization. However, these don't look like the same kind of number I held on the last problem, right? They're sort of already partially factored. Do you see that one? Especially the first one on this screen. 16 to the 4th, 81 to the 4th, and 6 to the 6th. But they're not in prime factorization notation. Why not? Because I've got numbers that are not 2 and are even, right? I've got a 16, which is not a prime number. I've got an 81, not a prime number, and I've got a 6, which is not a prime number. So far, so good? So what we're going to do is we're going to take a look at each of these individual numbers in this, 16, 81, and 6, and we're going to find out what their prime factorizations are. So I'm going to do this because I'm going to work with a small amount of space here. And I'm going to do that method that I introduced you to last time. What is the smallest prime number that divides 16? 2, which gives me 8, which is divisible by 2, which gives me 4, which is divisible by, which gives me 2, and then we're done. So right here, you find 4 2s. So this 16 right here is actually the number 2 to the 4th, but then there's another number 4 that was already there in the part of the problem. So I'm replacing the 16 with 2 to the 4th, because that's what 16 is in prime factorization. It is 2 to the 4th. Let's do the same thing with 81, but let's do a tree. If I was doing 81 with a tree, likely you would tell me that this breaks down into 9 times 9. And the 9s each break down into 3 times 3. So lo and behold, I actually get, this is a very beautiful tree because it's all at the bottom together. That doesn't always happen, but this one's a really nice one. So I actually get 4 3s, correct? So the location where you see the 81 can be replaced by 3 to the 4th, and then there's a number here that has to be included, and it happens to be another 4. There's nothing special about the fact that those both happen to have 4s everywhere. That's just how the problem worked out. But one other number, and you probably know what this number would work with. The 6 is actually the numbers 2 and 3. So this is 2 times 3, and it's raised to the 6th. That is far from simplified. But we're getting closer to what we want, because we see 2s and 3s everywhere as there's 16s, 81s, and 6s, right? So we're getting closer. We need to remember some rules from exponents from chapter 3. So then, what happens when I have 2 to the 4th to the 4th? Multiply, good. So this would be 2 to the 16th. How about 3 to the 4th to the 4th? 3 to the 16th, same thing, right? What am I going to do over here? I don't have an exponent to an exponent here. Yeah, we have this sort of ability to sort of distribute that exponent to each of the factors. So this is 2 to the 6th and 3 to the 6th. We're getting close to done, but why are we not yet finished? Okay, what about it is making you not finished though, in terms of exponents? I've got like bases. That's what's causing my problem. So I'm actually going to be combining some of those exponents. So tell me a like base that you see, Brenna. All right, so these two right here match. They've got the same base. So I've got a 2 to the 16th and a 2 to the 6th. How do I combine those together? I add the exponents. So 16 plus 6 is 22, right? And then I've got the same thing happening with my 3, right? 3 to the 16th and 3 to the 6th, which which is 3 to the 22 or 22nd, yeah. This is the simplified prime factorization notation. And again, there's really nothing special about the fact that they both had an exponent of 22 at the end. That will not always happen. What's different about C? There's an addition in here, isn't there? And that actually makes the problem quite different. Because you see, the addition means that, in fact, if you really look at it, the first one's already a prime factorization notation, and so is the second one. The fact that I'm adding them together changes something. Consider this, and let me just simplify it, do a simplified example. Let's say I had 2 times 3 plus 3 times 5. Each of those are both factored, right? But let's actually see what happens when I add them together. 2 times 3 is, 3 times 5 is, 6 plus 15 is 21, and 21 becomes 3 times 7. It doesn't necessarily look exactly like what I started with, right? I mean, it didn't even have a 2 in it at all. But let me show you what you can do with this very simple example that would give you that 3 times 7. Now let me just reiterate, you would not do this with this example. You'd do what we just did. But the problem is that what I just did there is not going to be all that helpful when I've got an exponent of 55. Is it? I don't want to multiply something out 55 times. So let me show you with this very simple example what we'll do with this more complicated one. Remember, our goal is going to be 3 times 7 at the end. What we're going to do is we're going to look at the two sets and we're going to say, do they have anything in common? They both have 3 in them. What we're going to do is we're going to bring the 3 out as a factor. So if I take 2 times 3 and I factor the 3 out, what's left? The 2. And if I have 3 times 5 and I bring the 3 out, what's left? The 5. And the addition sign doesn't go anywhere. It's still there. And what is 2 plus 7? 2 plus 5? 7. So there's that 3 times 7 that we got the other way too. Again, it's not really useful per se in that particular problem, but it's going to be extremely useful over here. Take a look at this. I've got 2 squared and I've got 2 to the 4th, right? They both have a factor of 2. In fact, how many matching factors of 2 do they have? They have 2 of them. Because there are 2 of them in 2 squared, and there are 4 of them in 2 to the 4th. So they each have at least 2. So I'm going to pull out a 2 squared. And when I pull out the 2 squared from this 2, there's nothing left. That took care of all of it. But when I pull out the 2 to the 4th, and I pull out 2 squared, how many 2's are left? 2 squared. There's still 2 2's left. Let's do the same thing now with the 3's. This one has 3 to the 5th, and this one has 3 to the 4th. How many matching 3's do they have? 4 of them. So this is 3 to the 4th. This was 3 to the 5th. I pulled out 3 to the 4th. How many 3's are left? 1. Or if you want to, you could write it as 3 to the 1 to remind yourself for the moment. This was 3 to the 4th, and I pulled out 3 to the 4th. They're all gone, right? I don't have any 3's left in the second term. And then what happens to my 7's? Not cancel, but they completely match, right? So I can pull all of the 7's out and not have any 7's left in either value because I've completely factored that bit out. All right. So let's take a look then at what we've got. These are already in factored form. This is 2 squared, 3 to the 4th, 7 to the 55th. This is the number 3. This is the number 2 squared, which is 4. 3 plus 4 is 7 today. And then I've got to combine something. This is a 7 to the 55th, and this is a 7 to the 1. So this is 2 squared, 3 to the 4th, 7 to the 56th. A little weird? Yeah, it's a little weird. But it works following the exact same principles as this very simple one over here did. I look for what they have in common, and I factor it out. And then I simplify what's left. All right, let me do this one. Let's see here, here we are. Let me do this one last slide, and then we'll stop for today. You guys can do group work. All right, last slide here. The fundamental theorem of arithmetic. I wanted to do this one because I already told you it. It says that each composite number can be written as a product of primes, and one and only one way, except that you can switch the order of the numbers. Right? So like 6 can be written as 2 times 3 or 3 times 2. But it has to be written with exactly 1, 2, and exactly 1, 3. That's the fundamental principle or fundamental theorem, depending on what research you're using, of arithmetic. Fundamental means it's awfully important, right? That's usually what happens in math. The word fundamental when it's very important. It's very concrete. And then the last one that we're going to do on this slide is theorem 414. It tells us that if D is a divisor of N, then N divided by D is also a divisor of N. Now think about this in terms of your factor trees because it works really well. All this is saying is that if you have the number like 432 and you break it down and you find a number that divides 432, 4 works. What is 432 divided by 4? What is it?
108.
108 is correct. All this is saying is that if 4 is a divisor, then 432, sorry, I circled the wrong thing for 4 over here. If 4 is a divisor of the 432, then 432 divided by 4 is a divisor. All it's telling you is that these occur in pairs. So if you get a divisor of 10, you're also getting a divisor of the number divided by 10. That's all this theorem says. I mean, and you guys know that to be true. You've worked with this factor trees for ages. Right? Since elementary school, you have this ability to break these pieces down. All right, we'll stop there for today.
All right, it's totally freaking out on me. I don't know why. I have new groups for you guys. Give me just a second. All right, Screencast schematics are working out. Let me put you guys in here. All right. This is your last set of groups. You guys know that. I'd like for you guys to make a note to yourself that we're about to, next week, we'll do it on Wednesday next week so that we have a chance to remind you on Monday. On Wednesday next week, we need to go through and start choosing when we're going to do presentations. You guys remember your presentations as far as this one was? Maybe you've had my class before, so this is not a surprise. But those are your like presentation. Wait a minute. Yes, you're going to do a presentation. There's details online about the presentation. I have no idea when I told you on the presentation that I said we were going to pick days. I have a feeling it was next Monday, but we'll do it Wednesday just so that everybody has a chance to really think about it. You need to look at 2 things. You need to look at when you'd like to do it, okay? Which right among the dates that are possible. And you need to look at which section you'd like to do among the sections that are possible. And all of that is underneath a link on our minority slide that says presentations. Okay, so you get all the details there. What we'll do is we'll randomly, I have a wonderful random number generator that I found last time. It's loads of fun on my iPad. We will randomly go through, I'll put all your names in, and it'll pull out your names one at a time, and we'll put them on the sideboard, and we'll go through it, everybody will pick their section number, we'll go through it, and everybody will pick their date, or vice versa, 1 and 2. So if you happen to be last on the first pick through, hopefully you're not last on the second option 2, so you get something you like. If there's absolutely something after we're all said and done, you flat out, you're the last person picking the one day that you happen to be out because you have a field trip that day or something like that. We'll work around that. We'll figure it out. But I think your classmates will get understanding. We'll make that work. You need to be present for all of those class periods for your presentation to your classmates, unless you have an excusable reason. And I absolutely hate having an attendance policy, but I don't know what
what else to do, most of the time it's not a problem with you guys. You guys just come because you know it's important that you should come to class because you're going to be teachers. But every now and then I have students who decide presentations aren't very important and they skip. These presentations are primarily forming the basis for your review for your exam. And there will be components that your classmates present which will be straight on the exam. So my final exam in this class changes every semester based on what people present in their presentations. So it is important both for that and for every presentation that you do miss, there is a deduction of points on your presentation score if you miss them and you don't have a valid excuse for it. So yes.
So the information of presentation is on.
Yes, it is. I think it may be at the very bottom of the middle room screen, like after everything else. Maybe at the very bottom.
And only needs like by yourself.
It's an individual presentation, yeah. It's just 10 minutes. It really is not a big stressor. I mean, but you're going to do it in one of two ways. Let me just say real quick. It's either going to be a smartboard presentation or an iPad presentation. And we can talk more about the details of the kinds of presentations after you've had a chance to read through the information online. So we'll talk more about it next Monday if you have questions. So try to make yourself a note to look for that information online and to read through it before next week, okay? And then we'll do the presentation choosing of everything on Wednesday. That way those who are presenting early on can go ahead and get started if they'd like. All right, Carly and Nicole, you guys are going to be partners for group work. Changing direction, we're not having presentations. Shelby's gone, but Shelby's going to be your partner, Brianna. Shelby sits behind Audrey normally. Isn't she in this class? Okay. She's in both of my elementary math classes. I'm trying to remember which class she sits where. Taylor, we're going to be working with Audrey. So you guys are right there together. No far moving. Taylor Melton and Sabra. Real close together there. Callie and Brenna, back at the back. And Avery, who's sitting in front of you. You guys are going to be my group of three. And then Katrina and Miss Taylor here at the front table. So for today, Brianna, you can join any group of two, okay?
Okay.
Go ahead and move around. We're looking at section 4.1. It's the only one that you need to worry about over the weekend to be finished with. We've got about 10 minutes to take a look at that information. Yeah, as always, if you don't know your partner, say, hi, my name is. You now know your partner. Well, I know you're good.
Yeah. Or like, oh yeah. Just list the ones that are
Was that a second submission, Brianna? Was that when you did a second submission or third? Okay, that, I assumed that everything. That's okay, that's what it was then, I assumed you last year.
Okay.
Sorry.
That's fine.
It's fixed now, though, so you should be able to see it correct.
The last two digits.
You just first, then work away.
5, 6. I can do that.
Yeah.
Well, if you divide it, if eight goes in,
This is for our example, we split up the
with
number.
one left over, bring down to eight, you get 18.
Every other one. True. Yeah, every other one. Yeah. I would think so. Some areas are different. Mine is express. Yes. This is A, so no way.
Say again?
Oh, yeah. Still needs to smell it. Yes. Yeah, that's true. You do like 7, you would say what, right? Can you take 0 items and divide them among 5 children or?
It's like, and you have 0 left over.
Minus 20 and 0, so 0.
No, it works by default.
It works by default.
So if you get a remainder, it's good. Yes. Yeah, I don't know why. Like, yeah, if it's I didn't think about mentioning that, I guess it's gonna work. But yeah, if it works at the rate here, it still works. It is, again, one of those things that's by default, it works. Okay, thanks. Okay, what's your number?
Yes, no, the sum of all of them. So 9 plus 18. Wait, 42. 5, 6, So digits are not right. So
Yeah, because I mean, obviously, 21 is more than 2 and 1.
there's 11.
The numbers.
Wait.
So the numbers of
So you've got 2 problems, 600.
Oh, yeah.
Right, yeah. possible.